if you can't explain it simply, you simply don't understand it. Those are the famous words of Albert Einstein. And the idea here is that if you can't explain something to a fourth grader, perhaps you don't really understand what you're talking about. And that's actually the challenge I often have. I do teach students public speaking. And one thing that we constantly do at an advanced level is try to describe something that is not visible. After all, when we think about the gurus of our time, whether they're in science, technology, or even spiritual gurus with esoteric ideas, they often use analogies as a principal tool, as the main tool to help us reach for things that can't see and then connect it to things that we do know about. So that's the big practice, and that's what I'm helping one of my students deal with today. For example, we talked about many subjects. Oftentimes, we think about other speakers that we use as models. We think about like Albert Einstein, how he used a sheet of fabric to model things like space-time, and how a heavy mass that pushes into that fabric of space-time could create a hole. And as objects get close to the hole, they naturally spiral down like those coin machines. And that's why we see the Earth revolve around a heavy mass like the sun. Likewise, we cover topics like even spiritual texts, and we talk about like how are parables used in things like the gospel. Like, whoa, that's another idea of trying to reach for things that are not visible. But today, we're going to try to talk about a topic that my student is tasked with, and that's electricity. Electricity is something that we do not see, but has a huge impact in almost every part of our lives today. So the analogy we're going to use is water. Be water, my friend. Water is a lot like electricity, and electricity is a lot like water. Why do we say that? Well, we use electricity in circuits to do all kinds of work. In the same way, you can use water to do a lot of work. Instead of using a wire, you can use a pipe. And instead of the flow of water crashing and hitting things, you can use electrons or the effects of electrons. You can use water in a steady state, just keep on pushing. That's the same as DC current. Or you could have water go back and forth in a pipe to do work. And that's what we call AC current, using waves. More than that, we can think about the idea of the three main factors inside of our circuits. When we have water, we have something called current, how much water is coming through your pipe. In the same way, we have current, electric current, which is how much electricity is coming out or through that wire or component. In water, we have pressure. We can be pushing things really hard and pushing a lot of current out with a lot of force. And then we have voltage, or the electromotive force, which is the same thing as pressure in electric circuits. How much stuff we're pushing out, how much power we're pushing with. And then, of course, we have resistance. In a pipe, you might have a thin pipe, or you might have sand in your pipe, some sort of obstructions, and that makes things harder to push. Likewise, we have resistance inside electric current. So, for example, if we have pure copper wire, there's almost no resistance. If you have gold, there's almost no resistance. But you have other materials, and now there's resistance. Okay, let's talk about something else. Let's talk about, intuitively, the relationship between pressure, current, and resistance. I mean, we all have experience sucking on a straw, right? That's like the voltage. But if we have, again, things inside there that obstruct the straw, we need this more pressure in order to continue the same current for a higher resistance. The more garbage there is in the straw, the harder we have to push the same amount of soda out of our straw. So that's something very, very intuitive, isn't it? And that's what's called Ohm's law in electricity. Likewise, we have circuits, and it's very intuitive. If you had a fork or a branch inside of your circuit in your water system, obviously the water coming into the branch, right, has to split so that all the current coming out of that split has to equal or sum up to the input. It's the same thing with electricity. All the electric current, all the electrons flowing, not really, but flowing through the branch or the forks in our circuit have to add up to the input. But if we look at a given point on that branch, we can see that the pressure is obviously the same at that one point, right? Because we're pushing right here. My mouth has the same pressure, no matter whether it comes from it branches into 2 straws or 1 straw or 6 straws. I'm still pushing with the same amount of voltage. So now we have this idea of circuit theory. What other things can we make an analogy for with water and electricity? I'm sure there are more that I can't even think of, but let's brainstorm. What other things can we talk about? We can talk about components. I have a small electric kit here. What's this? This is a resistor. If you crack open your calculator or computer or almost any of your electric devices or electronic devices, you'll see this thing. And we mentioned it before. It's like the sand inside your straw or that pinch point inside your straw, right? You can reduce the amount of voltage by using these things. Sometimes you don't want a huge gust of or pressure pushing on a component. If we think about a contraption that's powered by water, what happens if we push a tsunami or a tidal wave onto that contraption? It might break everything. That's why we put like a sand trap before it to kind of things dribble out into a level that the device can use. Or maybe we want to change some other characteristics of the energy coming out of that system. We use a resistor. Sometimes we want to split things and so forth. So that's one thing that we can do. Another analogy, resistors and like sand in your pipes, like a French drain, I guess you would call it. Another idea that we can use is this. Everyone might recognize this as a LED or a light emitting diode. And we can talk about how this actually works in the future. But let's talk about the analogy, right? A diode is a lot like a one-way valve, a flap. So imagine you have a pipe of water and you have a flap flowing in there, and there's a ledge here, right? If water flows this way, the flap can open up and let water go through. But if water flows the other way, that diaphragm or that gate is going to hit the flap and is going to be stuck. So water can only flow one way. It's the same thing with a diode. That's what a diode does. It forces the current to only go one way through a circuit. Let's talk about this. This is a capacitor. So what is a capacitor? A capacitor is a lot like a toilet tank, or a better example for me would be, have you ever been to a water park and then there's a bucket up in a high place and water flows into the bucket blip, 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 until it fills like the capacity of that bucket. And once the water stops flowing because something turned off there, the water suddenly tips back and it drains back into the pipes. That's what a capacitor is. It's essentially two big plates with a gap between it. So as we can think about it, when you have a circuit, if you close something, you break the circuit, nothing can flow, nothing works. But if you open it, now things can flow. The capacitor is like kind of like that bucket. So if you think about um, the voltage source as like a pump, or maybe your mouth pushing stuff right through the system, what's going to happen? So let's say we connect this to a large battery. The battery's pushing electrons on one side of the plate, and it's pulling or sucking electrons, or yeah, technically, analogously speaking, electrons away from the other side of the plate. So what's going to happen? The electrons are going to start building up on this plate, and it wants to flow to the other side, but can't because of this gap. But once we turn off or stop pushing or with our straw, what will happen? All of the electrons built up on this plate will suddenly drain back out towards where the pump was. So that's how you can think of a capacitor. It's kind of like that bucket that gets filled, right? And everything is normal, fill. And at some point, you turn off the pressure and boom, it flushes back out. And of course, just like a real capacitor, if you fill it up too much, it could burst. It could explode, right? Like a bucket that explodes. That's like what a capacitor is. And if you think about it, we talked about it before. We talked about direct current. If we're constantly pushing water one way, what will happen to a bucket? Assuming the bucket is very, very strong, right? The bucket will eventually fill up and boom, nothing will flow anymore once it's reached its capacity, right? The nothing will flow anymore because the bucket's full. But what would happen if we had like a alternating current? If we're pushing and sucking, pushing and sucking, pushing, blowing and sucking back and forth, the bucket would just go back and forth, and as if the bucket doesn't exist. For alternating current, a capacitor is just like a wire, it just goes back and forth. The bucket goes with the current. So that's the capacitor. Whereas if you constantly use direct current or constantly, say, blow into the capacitor, eventually it will be like an open current. And of course, you can do all kinds of things with capacitor. You can use it like as a temporary battery, where when it flows back, it actually creates pressure for a short time. There's so many tricks, more than I even know, but that is the capacitor. The capacitor analogy, like our flushing bucket or toilet. Let's think about another thing. Um, I don't have one here, but yeah, I don't have one. Inductors. Have you ever cracked open a computer or something and seen like little rings and there are wires wrapped around the rings? That's what we call an inductor. An inductor is like a water wheel, a water wheel. So if we think about a water wheel, maybe you've seen one in ancient times. They put a water wheel on a river, and the water wheel turns, and it's connected to something that grinds something. You know, we're using our brains to use the power of nature, right? And of course, we control that water wheel by putting a dam. And so sometimes you can have more water flushing into the water wheel and sometimes less, right? That's the idea of an inductor. So what happens with a water wheel? When we have water flowing through it in a direct way, the water wheel acts like nothing else. It's like a wire, right? Water's coming, the current's just going through the water wheel, it's going right through it. But if we stop the current, there's inertia, right? There's that momentum that keeps the wheel going. So that's something that's true about inductors, right? But what if we do alternating current, where we hit the blow, suck, right? This water wheel is going to be acting like a barrier because it's going to be everything's going to be stuck. The water wheel can't move, right? If we go fast enough, right? The water wheel. So it's now like an open current. It's like an open circuit, like a break or a cut, and nothing will flow. Wow, that's a lot that we've talked about in terms of um, this analogy between water and electricity. I hope this kind of gives us some food for thought. We can now look at our computer, our radios, our our calculators, and think about it. If I were to do this with water, could I? And in many cases, you could. There are other components that we won't go into that also use this water analogy, and there's some that the water analogy does not work for. However, I think that this is a fun thought experiment. You know, alternate. Obviously, if you were to give a formal talk about electricity, you would have to go a lot more in depth. However, this exercise of just thinking about analogies, even before you're doing a speech, can really be fruitful in helping you think about how to describe the unseen. In the future, I hope to carry this same analogy to other things in electronics. So maybe we'll talk about simple radio. How do simple radios work, and what analogy can we use for that? Other topics that were suggested by my students are phenomenon in outer space. We talked about nuclear fission. We'll talk about even crazy ideas like deep learning neural nets, which is going to require some research on my side, as well as things like blockchains. So, if you are interested in thinking about ideas um, in analogy without all of that complex mathematics, and please let me know. Write in my bottom comments, what type of topics would you like to explore in analogies? So thank you very much for listening, and I hope you enjoy this useful lesson. And I hope to hear from you in the near future. Thank you very much.